So now we are going to talk about something different and something that I feel like innovative and maybe, that may change the way that we measure the focus curve in any refractive surgery procedure. Let me start from the very beginning, talking about what the focus curves are. We know that they are subjective measurements for vision performances at different distances. And here is, for example, a binocular defocus curve of one of the trifocal IOLs available on the market. The focus curves may be done mono or binocular, we say. They may be performed correcting visual defects or without doing it. Basically, they all have a weakness, which is the subjectivity of the measurement, meaning that they measure other issues than purely optics, and they are examinator dependent. We will go on these points later. But what is the scope, the reason for doing the focus curves? Well, basically is to measure accommodation, and this is usually done to test like presbyopic correcting solutions. As I said, presbyopic correcting lenses or presbyLASIK or so. And here is the theoretical performance of an EDOF IOL. You see it in green compared to a bifocal and to a monofocal IOL. And this measure allowed the ANSI, the standard in the United States, to classify some lenses because they are able to give a certain amount of extension of the depth of focus compared to a monofocal IOL. So even from that perspective, the focus curves may be useful. What if we be able to objectively measure the optical properties, meaning without going through the subjectivity of not measuring the optics only, but the patient's features that are additional, like the pupil size, like the light conditions when these measurements are taken, or on another side, the real distance where these measures are taken, which may be a bias as well. So the focus curves is subjectively measured with lenses, we said, and this gives the amount of diopters eyes are able to read with or without correction. And the visual acuity is subjectively measured with eyes, unfortunately, and this is the biggest difficulty to overcome if we want to objectively measure optical properties of the eyes. So this gives the idea that I'm trying to explain today. While thinking about how to match the need of objectively measure this, the focus curve, Francesco Versace once more came out and said, I have an idea. And actually what we started doing is applying his idea to a project that is still very embryonic at the moment, but I think it may have a reason to be developed in future. So we know that the Paramis or Osiris aberrometer, call it as you like, it's the same machine, has huge abilities to give us, the optical properties of IOLs, for instance. If you compare the ability and the accuracy for measuring the aberrations of eyes who received a presbyopic correcting IOL, like in this case an EDOF, you see that you can really find differences among lenses, and you can really find details that are not measurable with any other aberrometers. Especially if you measure these differences using the dioptric power instead of the wavefront. Why is that? Because dioptric power is more accurate than wavefront. And I'll show you in a while what I'm saying. We know that spot function is one of the ways that we have to measure the performances of an optical system. However, point spread function relies on one data, which is the wavefront error. You see here in the formula, I'm not going to the details, but at some point it is WF and XY, that's the wavefront. So when we use a point spread function to define the defocus properties of an optical system, we unfortunately get less information just because the wavefront is not as accurate as dioptric power may be. And so here is where Francesco's excellent idea came in. So he said, why don't we try to find a way to use the same information that is derived from point spread function measurement, but given by the dioptric power instead of the wavefront. And so, researcher and finding, he found this very elegant way for measuring the properties of the lens, whatever it is, using the geometrical point spread function. So you see here, the geometrical point spread function does not include diffraction. It's a ray tracing method to simulate point spread function, which means that if you see here in the image, if you compare the details, let's say the accuracy of a point spread function versus the geometrical point spread function, you see how you may get more consistent information and less geometrical derived and more geometrical derived data than point spread function. For the same reason of obtaining more detailed data when analyzing the wavefront using the dioptric power versus the wavefront. And so you see here what Francesco ended up with on the left side of the slide. You see the measurement of a EDOF lens with a defocus curve ranging between -7 to +7 diopters. And you see here, really how the point spread function changes over this entire defocus curve. And you see here in the two following photographs how it is possible to define two specific points where actually the focus is more concentrated. And these two foci, in this case, are at +0.21 diopters and at -1.05, meaning that it is possible on an EDOF lens to measure the extension, the increase of the depth of focus. And here is where we are now. So we have a defocus measurement. You see this on the x-axis, and it is able to at least now we are able to measure and plot defocus, which is not based upon our lenses to be put in front of the eyes of our patients, but derived objectively. What about the visual acuity then, which is the most challenging point at this? Because if we are trying to do it objectively, we cannot rely on patients. We cannot rely on other functions like, for instance, the macular ability to solve the light and so. And again, Francesco was elegant to find another mathematical model. You read here the spatial frequency cutoff of radially averaged optical transfer function, which has been published by Larry Tibos many times in the past. Obviously, I'm not going through all of this because, Francesco, if you like, you can come here and explain the audience what is this exactly. But the most important point is that what the spatial frequency cutoff of radially averaged optical transfer function gives us the possibility to give a cutoff on this kind of measurement and define what the performance of visual acuity may go through. And you see here what we have at the end. So we really have a defocus curve, very nice, very elegant, with a defocus power, like for diopters on the x-axis, and a visual acuity, obviously objectively measured and not subjectively measured, so totally independent from the function of the eye, to describe that optics. And you see here how this defocus curves, two different, same defocus curves, but these two different measurements. I go back to the peak of distance, and I go to the peak of intermediate, really describes how are the optical properties of this specifically EDOF IOL that I'm not going to disclose what it is just because it's not nice and polite. So let's open the ground about the potential possibility of it, because now we have the possibility not just to, as we said, measure what the eyes of the patients are doing in terms of extension of the depth of focus. We have the possibility to bring patients in front of the Osiris, or Paramis, call it as you like, and objectively measure what is their defocus. And I think this is very interesting from many point of view, because this may open the possibility to standardize measurements also according to different conditions, like the light, like the pupil size, and really assess whether these parameters have an impact in patients' performances when measuring them after, for instance, the implantation of presbyopic correcting IOL. This kind of measure may help us as ophthalmologists to really understand what is given by the optics of the IOL that we are going to choose to be implanted, and the anatomy of the eye itself. Because we know there are many other factors than the optics properties of the IOL, which lead to the final performance of the patient when reading at near, at intermediate, and distance, like the corneal curvature, like the pupil, like the anterior chamber depth, and all of that. I really think that this may increase also the consistency and the accuracy of the defocus curves, which may not be biased in this case by the patient and by the way that we subjectively measure it. And also, in a theoretical future, these kind of measures may help us as clinicians to choose the best IOL to be implanted according to preoperative values that we measure, like as I said, the corneal curvature, the pupil size, the anterior chamber depth, as to really customize not just the IOL on a theoretical performance, but on an objective performance that the IOL may have on these individualized eyes. There is a weak point, obviously, because what we can do today with the Paramis or Osiris is measure one eye at a time, but I'm sure that CSO has something in their list to present, I hope soon, and overcome this downside of being able to measure one eye at a time. So this slide represents very well what happened in the development of this original idea. I just went to Francesco saying, Francesco, this is not my job, do it, please. And so I want to credit him about all the job that has been done, and I hope it's going to be followed by CSO in future. And I'd like to thank you all for your attention and for being here this morning. Thank you.